All right. Thank you very much for having me speak to you this morning. I will be talking about galaxies, and so I don't know if the room is dark enough, so you might have to use your imagination occasionally. This is a science domain project, so it's going to have an answer. I'm going to try to have a scientific understanding at the end. I'm going to have a process that goes along the way. And I'm actually going to hit a lot of areas that came up during the previous discussion. I hope I hit a lot of areas that came up in the previous discussion. But the main goal here is to understand how galaxies formed and turned into what we see today. Most of the understanding we have about galaxies in our universe come from what we see today. And there's a lot of effort that goes into understanding galaxies. Don't worry too much about what's going on here, but there's a lot of things on this to understand how a galaxy evolves. It has to do with its gas mass, its dark matter mass, its speed of rotation, whether or not it sits in a filament or a void, its black hole at the center, all of these different things. There's a lot to do here, right? So this is a big science area in our field. And I will focus on one very simple piece of this. So I promise you I will not untangle galaxy evolution for you today. That would be a different talk at a different meeting. But I will do one little thing, and I will focus on this, and I will be focusing on the shapes of galaxies, and I will be using the data that astronomers use to solve this problem. And I will bring AI into this and show how we've made a leap, we think, in understanding of what's going on inside these galaxies. So let me start out with the challenge that we're facing. This is some sort of spiral galaxy that's sitting out there. It's a nice big near one. Hopefully you can see those arms. And with the data we take for these things involves a spectrum. And I have over there something called spectral resolution. If I just took a picture of this thing on a camera and put a filter in it, like a red filter, that would have a spectral resolution for us of 1. It's just a giant red box. Is it reddish or is it bluish? And then I can actually put a grating on and a grism and a prism. I can do all kinds of great stuff to do a higher resolution. Typically, we tend to use just the colors of these galaxies. I'll show that in a second. The other issue is what we call imaging resolution. So you can see the arms there. It might even look a little fuzzy to you, but our atmosphere blocks out stuff, and blurs things out. We have issues with instruments. It's a challenging thing for us to do. And so in the end, what we often have is a case where we add up all the light of some fuzzy thing that sits inside that blue circle, and that's what we work with, okay? So the modern understanding of how galaxies form and evolved is really based on are kind of the worst we could do, but it's all we got. And I'll explain why that's all we got for the moment. First of all, we need millions of these things, but it's a hard thing to do. So what do we do with this? The example I'm going to use is using the light in this box, in that circle there, to make an estimate of the stellar mass. And in these plots here, don't get too worried about the details. There's a mass on the x-axis. That's what I'm going to care about. And then there's a measurement on the y-axis, and that is basically I take a picture of a galaxy in a blue filter and a red filter. And if it's more red than blue, I call it red. If it's more blue than red, I call it blue. And so those two clumps there are red and blue galaxies. I know, don't laugh at me, but they look like there's linear relationships there, because that's what we do. We say there's a linear relationship there, and we then work with that. So I know this sounds terrible from a science perspective, but it's really what we do, okay, to understand galaxy evolution. Because we can't measure that x-axis without some really hard work, but we can measure that y-axis quite easily, okay? So that's why this science has taken so long to get where it is because of the challenge, the experimental challenge that exists in it. So one more detail on the experimental challenge. Here's a fuzzy blob. This is a galaxy that sits in there, and there's a red circle and a blue circle in there. And these are where I would sit down an optical fiber in an instrument, a very fancy instrument, a multi-million-dollar instrument on a $100 million telescope, and I'd sit a fiber down on there and I'd collect that spectrum on the right-hand side. And that spectrum, that's the thing that's going to tell me the stellar mass of this thing, right? So this is really hard to do. This takes a lot of time on a very expensive telescope. And my fibers, those are the size of optical fibers. I can't fix that, right? And so that's just the engineering challenge we have. And so we've been working with data like this to build models of how galaxies evolved, and we make scientific decisions on that. And we feed these back into simulations, and we do theory, and we do all kinds of great stuff with this. We think, that's what we're trying to do. So this is the issue we have. So things changed in the last 10 years. So where they've changed is that we designed an experiment. We did not use AI like Mario did to design an experiment. We just did the dumbest thing we could do. And we said, you know what? One of those fibers isn't enough. What if we just built an array of these things and plopped them down under these galaxies? And now we can get a spectrum all over the place. Because in this picture here, you'll notice where I put the blue versus the red, those spectrum on the right look totally different, and I would get totally do measurements of a stellar mass in that region for this galaxy. This galaxy has a total stellar mass of all the stars in it, but depending on where I look, I'm going to get different estimates of what that is. And so if I'm going to map that out, I'm going to build what we call an integral field unit. So this was an experimental novelty that came out maybe 10 years ago. They're, again, very expensive to make, very time-consuming, and this is all the rage in astronomy right now. If I try to go to a telescope and get time on one of these things, I might get a night to observe a few galaxies. That's not going to help me in terms of understanding the evolution of galaxies. So a survey came out. In astronomy, we do surveys that was dedicated to do this over 5 to 6 years and just sit on thousands, not that many thousands, but a few thousands of these galaxies and collect this data. And so that's our data set that we have now. We've leapt forward in time from having just to use colors, but we can do those for millions of galaxies, to having a few thousand that we can get data like this. Okay, and so all these galaxies now have some coverage, and these maps that I'm showing, I'm going to focus on this one here. All of those pixels in that image are a measure of the number of stars, solar stars, basically, that exist in that galaxy. And what I would like to do is I'd like to say, since I can't get these spectral data for all other galaxies in the universe, that's too expensive for me to do, but I do have pictures of all these galaxies in the universe, I'd like to find some mapping between the pictures and that spectral data, okay? And that's what I'm going to try to do. Now, what's happening underneath in AI? So this is a short history of AI all the way back from Watson. You can see somewhere around 2015, this is what I care about, TensorFlow comes online. And now we're into the large language models and things like that on the right. Astronomy tends to lag these things now a little bit, but here is the rate of the number of publications related to many of these topics over time, up through about 2020. And you can see here in about 2018, 15, we're not doing much with TensorFlow. But by 2020, people in astronomy are starting to pay attention to something like this, right, for their analyses. And so in 2018, we're watching the field and we're starting to think about, hey, how do we get to play in this game as well? I'm an astronomer, I'm not a computer scientist. How do I make this happen, all right? So the way I made it happen was I recognized what they were doing. So me as the scientist says, there's something called this CNN. It works great for, like, I don't know, finding deer in images that self-driving cars don't want to hit and stuff like that. I don't care about that. I care about finding star clumps in galaxies. But I do recognize it as a way to be able to possibly predict these pixel-level stellar masses from the photometry alone with a complex model. I can't do it. I don't know how to do it, but I know I want to do it. So at Michigan, we're very lucky. At Michigan, we have lots of programs to help us with this. Michigan is one of these universities that has what's called a dual degree program. Our engineering school and our College of Literature, Science, and the Arts are separate schools. That means you cannot double major in, say, computer science and astronomy. That's not allowed, unless you're in something called the Michigan Dual Degree Program. And some students get accepted into that program, and we had one. So we had a student who was a CS major in the engineering group and an interdisciplinary astronomy major on our side. He had also been talking to us through a program that Michigan offered that some of you in the room may remember. It's called M-Cubed. M-Cubed was a way for the university to fund starter projects that helped you. They didn't give you a ton of money, but they got you started thinking about how to do science in an interdisciplinary way. We met Jai-Lei Huang. He had this interest in using TensorFlow. We had the interest in doing astronomy. We bring it in and we get started on this. So we made some great progress right away. As anybody in the room that does domain science with AI will tell you, it's not really about the computer science, it's about the data. So you spend about a year just munging data to try to get to where you need to be. And in a year, we did great. We had an answer. I'll explain this in a second. I'll come back to it in a second. Don't worry about it, but we did great. However, the key to this is the project stall. So why does the project stall? Because if you're a domain scientist like me, those guys leave. They leave astronomy because NVIDIA is going to pay you more. So he goes to work for NVIDIA, and he disappears, and I'm trying to keep him involved in the project. It's hard. I can't. He's literally like down on the floor of a car driving around San Francisco, coding into his NVIDIA while he's talking to me on the phone, talking about, it's crazy, right? Didn't last. Pandemic hits, everything stops. I'm trying to do this myself. In astronomy, we use Python. I'm not a TensorFlow person. Just isn't working for me. So another program helps me out at Michigan. Michigan had an institute with Shanghai Jiangtao University in China. I had visited there a few times to try to develop interdisciplinary relationships, and I was there in 2023 after the pandemic, and I'm giving a talk on this, and I meet a student over there who wants to visit Michigan and get started on this project. So it's a second Michigan connection that allowed me to move forward on this that I couldn't have done just on my own, okay? So he visits. The first thing he says is, we're not using TensorFlow. We're switching to PyTorch, and PyTorch at this time is kind of leveling out with TensorFlow if you're paying attention to this stuff. But here's the thing about PyTorch, it's Python. Right? And so it's doing the same thing, but now I know how to code it, and I know how to program it, and I know how to participate. So I'm much more engaged in the day-to-day research that's happening because it came to my language instead of me going to the other language. So in the end, our plot looks like this. I don't want to go into too many of the details, because I'm going to explain what this means in a second, but this x-axis and y-axis, there's a truth in the labeling data set, and there's a prediction. And these numbers on these axes just represent these stellar masses. So the difference between the red and the blue on here is that the red is where I've made an estimate in these pixels of the stellar mass from the light alone, from the pixel images alone, no spectrum. I've trained on the spectrum. And the red says sum it all up in a circle. Okay? So take everything within that blue circle and more or less recreate what's been done before, but use our model. Don't use one of these dumb linear models that we've created in the past. Use our CNN model. It does great. The red does great. The fun part is the blue. The blue says, actually, we just care about the individual pixels. We don't care what galaxy it lives in. So that's the new part. We've never been able to do that before at all. And I'm going to show you that if we tried to use our old models to do the blue, in fact, we just do badly in everything. So if we look at how we did this before, if I use those models, I get something that looks like this. Those old crappy linear models, pardon my French there, do not work. So something changed, okay? So the CNN is a nonlinear model. We know that. I'm not surprised by that. So yes, we move from linear to nonlinear. Can I learn something else from this? What is going on here? And so this is where the understanding comes into work. So now we sit down, and I'm not going to gain any trust in my community if I just throw the model out there and say, trust me, it works, use it. It's not going to work. I can't compete like that. I've got to compete by explaining what's going on. And so what we do is we spend some time looking at these things, and this is what you do when you're doing domain science with this stuff. You just look at the data all the time, and you're trying to figure out what did it learn and what did it do different. And so here are an example of an image. You know, there's just a filtered image on the left. The truth here is the stellar masses in these Voronoi tessellation cells that we had to learn about is very complex. And then we had a model prediction, and we have a comparison on the right. So there's some fun stuff that we figured out. So if we bring in this thing called the Bell prediction in the third column here, this is that prediction that comes from these very simple linear models from the colors that I showed you at the beginning of my talk, okay? So I go to the pixels, I measure their blue versus red colors, and I compare them, and I make the stellar mass prediction, and I get back a spiral galaxy that looks just like the spiral galaxy I put in, okay? It's mapping directly to the image. But if I look at the truth or the model prediction, those spiral arms are not there, okay? So that is what I'm trying to learn, and I'm being fooled by thinking those spiral arms are important to my model. Structure is very important to my model, but not that structure. That is kind of the human eye being fooled by what's going on. So we decided to play a little game with this and say, okay, we know we can do this. This is all the way down to individual cells in any galaxy randomized. We're getting it right incredibly well. These are orders of magnitude and masses. But if I apply that linear model, I do really, really poorly. How can I learn how I got there? Again, I kind of do the dumbest thing in my head. I basically say, remove the structure in these galaxies. And this is what we do. We take these galaxies and we start scrambling or smoothing out the structure. And as we start smoothing out the structure, we delete all of this correlation that we had before. So I don't know the model that describes that structure. I cannot write it down. A machine can write it down. Right? So that's the thing I've learned, is that the structural dependence of where these little pixels live, knowing that you're next to a bulge in the galaxy or next to a spiral arm or next to a filament, that structure is incredibly hard to write down, if not impossible for a human to write down, but it's not so hard for a machine to figure out. Okay, so now I think I have some trust built around this. So what have we learned? So one of the things we've learned is we've learned that we have ignored this idea of structure inside these galaxies in modeling how we get stellar mass from these color properties, that we can do much better. Now, we haven't solved galaxy evolution. We're just at the very beginning of the stage of saying we have to think about this differently now. Okay, what we had before was that the color of a star was all we needed. That's not true anymore. The position of the star and its environment matters just as much, if not more, than the color of that star. That's a new way of thinking. So we've learned that. And we've learned that everything we did before, that it's not that we've got the science wrong. Definitely won't say that. But I will say that every time we've tried to extend this down to smaller masses and smaller clumps and further distances, we've been making assumptions that we can now show are incorrect. I'm not saying we got the science wrong. We might have gotten lucky. Humans are smart, right? But I am saying how we went about it is definitely incorrect, okay? We've learned that the CNNs are doing the things that the human mind can't do. I would love to be able to write down for you what this spatial covariance model is, but I cannot, right? I will dig through these filters. I will dig through these layers. I promise you, that's on our list to do, and see if we can learn more about it. Maybe we can identify a filter that identifies the spiral arms versus a filter that identifies a clump versus a filter that identifies a bar, and I can start making some deeper understanding of it. But what I know now is that spatial covariance is in there, and it matters, okay? So this is going to lead, I think, to a paradigm shift in how we think about galaxy evolution, and the machines helped, right? They did something we couldn't do, okay? So the journey itself, some things we learned about the journey. So these tools that we use, I was just at another AI conference down in Patagonia, and I'm listening to all these great new tools for astronomy that come out, and I'm still using PyTorch from 2020. Crying out loud. Just slow down, everybody, right? So I understand the desire from a computer science perspective to push forward, right? But as a scientist, I'm way slower than that, and teams are way slower than that. So science tends to work at a pace that's slower. And often that's because these projects are not funded, because I don't know what I'm doing. I don't know where this is leading, right? I'm exploring, and exploratory projects are often the least funded projects that are out there. So science tends to run behind, right? And it is a question, can we fix this, and should we, and how do we do this? This idea of like the M cubed thing that Michigan had here was a very simple way to go after that and try to fix that. Maybe we do more of that. So leveraging the human population. So this idea of finding a student who had the computer science background and was driven to use TensorFlow to get a job at NVIDIA, while at the same time having a deep domain interest in astronomy. Those are special people, and that helped. That helped a lot, right? And so from a domain science perspective, the separation of powers is not probably how you want to, at least on the science side, go forward. You need to find the people that, that pie diagram, we've heard about that before. Okay. And of course, at some point you need to spend the time convincing your fellow scientists that this stuff, when it works, I understand you don't want to trust it. Scientists are not very trustworthy people. So that's our job. Our job is to basically make sure that what's coming out, it really works, and we test and test and test. So we're, at least in astronomy, we're at a stage where we're still trying to convince our colleagues that this stuff is really doing what it needs to do. So building trust into the analysis project is paramount to getting these things moving, at least in astronomy. Okay, and I have to be aware of the shiny new toy syndrome, right? Every time there's a new fancy thing out, I need to focus on what I was doing before and think about why I was going after it. Okay, so the human network here is vast. Okay, and we loved being able to work in a place like Michigan where we had these facilities and these resources to do this kind of stuff. Okay, thank you very much.
So, historical comment. So, applications of AI and machine learning to astronomy are not as recent as you started. They go back at least to the late 1980s with the AutoClass project, which found categories of stars that we didn't know about, to the SkyCap project, which built decision trees to distinguish stars from galaxies. So there's a long history of this. And talking about using old technology, I think you should go back and look at some of the older technology, which is much more understandable, much more robust. Not as sexy, maybe, but I encourage you to consider it, because I think that there are advantages to it. But my real question is, astronomy has always been a data-centric science, because it's relatively easy to observe all these things. And of course, as resolutions increased, it's become even more focused on that. But there's also strong theoretical and modeling aspect, which you didn't talk about. And we can use AI techniques to search a space of models, particularly explanatory models of galactic evolution. And you didn't say anything about that, and I hope you can say a bit about that side, because science is not just about data. Science is about relationship between data and models. And when I say models, I mean scientific models, not a neural net model.
Right. So the challenge of galaxy evolution is built around starting stars off, which is gravity. It's around how gas interacts. So there's real physics behind all this, right? So the challenge in astronomy, and I'm actually more of a cosmologist than a galaxy evolution person, but I have the same challenge, is that most of that theory are rough sketches that go into simulations, right? And so if we really want to understand how stars form and how galaxies collect those stars in a gravitational environment of an expanding universe, really the only way we're doing that is through large hydrodynamic simulations of multi-scale, right? So we feed those information, and the information that we have to feed those simulations is coming from somewhere else, right? So we're not doing it from first principles. It's just not the case. We're just not doing it from first. We don't know the first principles. We don't know the initial mass function. We don't even know the local environment. Gravity is a nonlinear process. It's an n-body problem. We don't know the environment. None of these things work like that.
You know traditionally that people go into these really expensive computer simulations, but there is lots of work in AI, particularly in an area called qualitative physics. Your colleague Ben Kuipers here is an expert in the area, where you can describe models of complex systems at a qualitative level.
Yep.
They make predictions, and you can compare them data. And I think that might be a better fit to the kind of situation the field is currently in. And you may want to talk with them about it afterwards.
Yeah. So part of that. So the end result of the spatial correlations is it's a parameter. It's a parameter that's been ignored through all of these, right? So could we have found that through some other way? Maybe. I mean, so that is a question. Could you have searched for it in a simulation, perhaps, and found it and discovered it in a different way? But at some point, you're only going to make so much scientific progress with the human in the loop that's actually kind of noticing that these things exist.
The work you've done is great.
Yeah.
Okay? I just want to make sure that we don't forget about the models. It's not all about the data. Right. Good.
Hi, very cool talk, thanks. You have a problem, you investigate a problem that I also find very interesting, namely seeing what the machine has learned inside. So I'm curious, what are the best ways that you have discovered? What are the best techniques to see what the machine learning models learned? So
in our case, to understand what's going on inside the machines, my only experience is with something like GradCam. So it's basically, you're basically following the activation maps back and things like that. And I think of GradCam as a tool that basically allows you to say, where did the machine, as it's going through its CNN, spend its time? Where did it learn the most? And so as an example, we do galaxy classification, and we ask, is a galaxy a spiral or is a galaxy an elliptical? And what we learn is that the human eye, when we ask the humans focus on the spiral arms. They look at a picture and they see the spiral arms. However, the machine doesn't look at the spiral arms. Oddly enough, in a spiral galaxy, the machine looks at the core where there are no spiral arms. And we learned that by using GradCam. And the opposite is true for a galaxy that has no spiral arms. It spends its time in the outskirts where there are no spiral arms. And we found this to be quite interesting. I can't talk to the machines and ask the machines why. Why would you do the opposite of what I would think you would do? But we surmise that what's going on is that the machine is actually doing calculus, right? That we didn't ask it to do. And what it's doing is it's looking at light profiles as well as spatial features. And so when we train these things and we say these are spirals and these are ellipticals, the machines are also learning that there's a simple light profile. It's steeper and more bright in the core than it is at the outskirts in spirals versus ellipticals or vice versa. And it gets more information out of that than it does out of the arms. And so it spends if it sees arms, it's moved on to the next thing. But if it doesn't, it spends a lot of time doing calculus inside the light profile. So GradCam has allowed us to see what the machines are doing in that sense. But again, we still need the human to figure out what's going on. It's not as easy as from that step. We spent a lot of time just figuring out why.
Hey, good morning. Just a quick question on the data portion you mentioned earlier. Could you describe what exactly you had to do to prepare the data? Like, I'm assuming a mass amount of data.
Right.
And two, what you did to validate for the data integrity part in that year you mentioned on the start install. Thanks.
Right. Yeah. So I will rephrase that a little bit in terms of the data challenges and how we overcame them, if that's okay. And I'll try to get to all those pieces. So these data are kind of new data for astronomy. Data in astronomy has usually been two-dimensional images with pixel values, single values, like flux in some sort of filter band, or a spectrum of a single object. And so now we have data cubes. And for a lot of fields, data cubes aren't a challenge. But for astronomers that aren't used to it, data cubes are a challenge. So most of the tools that we needed hadn't been written yet when we were going to after this. And so we had to kind of build tools or use these precursor tools to analyze these data and get to these data cubes. The data are pre-processed by another team. So the survey team that provided my truths, these stellar masses on these axes, these truths, were these model fits that someone had mentioned earlier. Those are these spectrum within these little pixels that have been fit to complex models to get a stellar mass. And we had to learn, we know about these, but we have to know these models very carefully. There's dozens, or if not 3 or 4 dozen of them in the literature, and we had to understand why they chose. The difference between these two is just 2 different models of stellar masses that live underneath. One of these is based on without physics, and one of these is based on pure physics, right? That goes in here. We had to learn those things. We also had to learn that the astronomers had decided that the way they wanted to present their data to us from these surveys is in bins of constant signal to noise, which means they took their giant cube of all those fibers, recombined them into these Voronoi tessellation cells so that they reached the signal to noise and then send that off. And we had to manage with that as well. So there was a lot of details that had to be assessed when you go in there. This is your data munging issue. In terms of validation, what we have to do is then make sure that, first of all, this is part of the validation, making sure that our model at least gets back what they told us it should be. But then we have to go out to the literature and we're doing some sort of, bootstrap test to make sure that we are not in complete disagreement when we use these things in other ways. So we have to check our colors, check our masses. So as the domain scientist in the room, that's more of my job to basically just continue down the list of tests to make sure these things work and make sense. And so I think that's probably how most domain scientists work. We'll find out when we hear from the other 3. I hope I got to some of your question there. Thank you.